This one here can be kind of tricky. It is not p-test because it's not to the nth power. The 2 is to the 1 over n power. So that makes me think t for d. Because it's not geometric, it's not a p-test, so let's just try taking the limit as n goes to infinity of this. And then if I put the infinity in here, I get 2 to the 0. Oh, 2 to the 0, that's 1. All right, since this doesn't equal 0, therefore I know that the whole thing, you need to write this, nth root of 2, make my sign better, diverges t for d. This here does look like a p-test, but because I see the addition in the numerator, I know I need to separate it. So I'm going to separate it into two sums. This one converges right away, p-test. I can see it. This one here, I'm going to take the time to pull the 2 out just so I can clearly see, oh yes, that converges by p-test also. And so therefore, the whole thing converges. This here has a positive 1 in the denominator. We can't do what we just did here. We can't split it up. It's not looking pretty. So again, when there's nothing that immediately comes to mind, I'm going to try t for d. I take the limit as n goes to infinity, n over 3n plus 1. It's not necessary to use L'Hopital's. You could just take the highest powers, and that gives you 1/3. Oh, it doesn't equal 0, so the whole thing diverges by t for d. Okay, so I am going to be telling you when to use the integral test, and many times it's going to be when there's e's and ln's. So it is necessary to start by rewriting it, and I started at 2 only because ln of 1 is 0, and that wouldn't be good. And I have to change it to x's. So I'd have x, ln of x, and you see that an easy u substitution will work. That'll be the hardest the integrals get. So the next thing I need to do is I need to rewrite this t to infinity. So I have 2 to t, and I'll just carry that 2 along. And then you can see that that's the root ln of x, and the 1 over x dx gets taken care of. So I get a u to the negative 1/2. So you have to be careful. Remember to put the x's back in before you take the limit. So actually, let's go take the integral. So I would get 2. You know that would give me u to the 1/2 over a 1/2 or times a 2. And then right now, I'm going to put the x's back in. Oops, t's to infinity. So I get 4 root ln of x. And then I'm going to say from 2 to t. So this is a necessary step. So I'd have to say limit as t goes to infinity, because I'm putting this in, right? 4 root ln of t. Subtract 4 root ln of 2. So be careful. You make sure you write this step. And then you see, oh, ln of t, t's going to infinity. That's infinity. Root infinity. That's infinity. So it's infinity. So since this integral diverges, therefore this sum diverges by integral test. So let's look at this next one. Again, I'll tell you when to use integral test. So this one, I first start off by writing 1 to infinity, change it to x's. And as I'm changing it to x's, I'm going to take that e that's in the denominator and bring it up. So I have limit as t goes to infinity. And I see that I'm going to do an easy u substitution. Again, that's as hard as the integrals will be. Negative 3x squared dx. So I get a negative 1/3 e to the u du. And then let's take the antiderivative. And you know that's e to the u. And so then I'm going to put the u back in between 1 and t. Oops, I forgot to put the 1 and t here. Okay, so now again, it's important, I think, to rewrite this as the fraction that it is. So if I carry along the negative 1/3 and rewrite this as 1 over e to the x cubed before I plug in the 1 and the t, then it's going to be really clear what happens when you plug in the infinity. So I get 1 over e to the t cubed, subtract a negative, 1 over 3, and then I just get an e. Now put the infinity in for the t. This whole term goes to 0, so I get 1 over 3e. So that means this integral converges, and so therefore this converges by the integral test. Okay, so this one here, I wanted to make sure that you have to write out what the S sub n is, because I know you can figure out the canceling pattern, but I want you to show me all your work. First step is, again, to do partial fractions. N plus 1, n plus 2. You're expert at this from last section. So I get 3 is equal to n, a times n plus 2 plus b, n plus 1, oops, b. So then I'm going to choose the wise numbers, right? So let n equal negative 2. So if I let n equal negative 2, that gives me 3 equals negative 2, that's gone, and so I get a negative b, so then b is equal to a negative 3. All right, now I'm going to choose let n equal negative 1. If I put n equal negative 1, this term is 0, and so then here I get a is 3. So a is 3. This happens almost all the time, that you get opposite numbers. Okay, so now let's make sure we put them in the right places. And again, I'm rewriting the sum, right? So this sum turns into the sum of 3 over n plus 1 minus 3 over n plus 2. So this is where you have to be careful not to split up the sum, but now it's your job to find out what the S sub n is. And the S sub n is the sum of the first n terms. So that means I'm going to start by plugging in n equal 1. So if I plug in n equal 1, I get 3 over 2 minus 3 over 3. Okay, then I'm going to plug in n equal 2. That's the next one. So 3 over 3 minus 3 over 5 plus, and I'm going to plug in n equal 3 plus 3 over 4. Oops, I started to write plus, don't want to write plus, minus 3 over 5. And then we've got this major dot, dot, dot land, right? Maybe I'll just write one more, because I want to make sure you really see the canceling pattern. N equal 4, 3 over 5 minus 3 over 6, dot, 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 dot. Okay, so I can write out what the nth term is, because the nth term is just that. Minus 3 over n plus 2. So the one before it is me plugging in n minus 1 into here. So that gives me 3 over n minus 3 over n plus 1. Okay, so now let's look for the canceling pattern. So 3 over 2. That looks like it stays. This cancels with this. And then... oh, hold on. N equal 2. And then this cancels with this. And then, oh dear, I made a mistake. Hold on.